Yeah, and now I have the honor to introduce our last speakers, Wim Wuyts from Gpixel. And well, he will tell us about 3D sensors, latest CMOS image sensor developments for 3D imaging. So please,
thank you.
The stage is yours.
Thank you everyone for joining so late. So indeed, my talk will focus on image sensors, and we are an image sensor developer. So I will talk a little bit on which image sensors goes into which 3D applications and for what reasons they are. And I will also shed some light on the future development and what is coming up next from the image sensor point of view. So a quick outline I just mentioned. So we'll first talk a little about Gpixel, and then I will focus on which products we have for three particular 3D methods, being laser triangulation, structured light, and time of flight. Very quickly on Gpixel, for those who doesn't know us, we develop CMOS image sensors, both off-the-shelf and customized solutions. And we do that typically for industrial markets today, otherwise we would not be here, but also for scientific and professional markets like video imaging and so on. So we are, from a number point of view, we are about 10 years on the market here. We had a nice growth so far, so we are doing well in the industrial market, and today we see that the 3D imaging definitively is one of our growing points. You also see here that we do both standard and custom products, so it's kind of a 50-50 split. And from a regional point of view, since the company was started and the headquarters is in China, there is quite some business in China too. Today we have 3 offices, so we have 2 office locations in China, and then we have an office in Belgium and in Japan too. So as I already mentioned, we serve different markets. Industrial imaging or inspection is for us today the most important market. That's a lot of factory automation, inspection applications, typical machine vision, both with area scan, line scan. We started actually in the scientific space, so a lot of imagers for life science, astronomy, those kind of things. As I mentioned, we are also serving professional markets, so that's photography and video, and then we do a bunch of other stuff, such as traffic, high speed, and so on. This is the current product portfolio, which is rapidly growing. We kind of divide our different products with names tailored to an application, as you see. For instance, G-Sprint is our high-speed product line, so for obvious reasons. And then GTOF would then be our time-of-flight image sensor products. So enough about Gpixel as a company. I'll talk a little bit about 3D imaging. I found some nice pictures from Zivit actually on the web, just to explain the different techniques. So in short, this is just to explain briefly the different techniques that you can use. You have laser triangulation. We have structured light with different illumination techniques. And then we have time of flight. So I did not include stereo vision in this presentation, but that's obviously also a way to do 3D. If we talk first about laser triangulation, just as an introduction, so it's probably one of the most popular modes today. Commonly used in 3D imaging for industrial applications, applications such as PCB inspection, logistics like parcel sorting, road, railway inspections, and yeah, 3D inspection in general. One of the main advantages, obviously, it's a good fit for conveyor belt applications and inspection lines that are passing across a company, a product, and it's a quite relatively simple measurement principle. One of the key disadvantages of this technique is that you have the measurement speed is actually tied to the conveyor belt speed, so that can be relatively slow, and there is no color information. If we then kind of derive the technique to the needs of the image sensor, Typically, you would then end up with image sensor specifications like a global shutter, because of course things move, so you need to try to freeze the motion. You need, as much as possible, horizontal resolution, because you look to the conveyor belt, and much less vertical resolution. So it kind of is one of those applications where a aspect ratio of 1:1 is not so suited, so you typically have aspect ratios which are 2:1 or any other even wider applications. Of course, you also need to increase the signal-to-noise ratio of your measurement, and that's typically done by having as large as possible pixels, because then you have a large full well, and then you can make a nice measurement with a high signal-to-noise ratio. Of course, throughput, the sensor needs to follow the speed of the measurements, so then we talk about frame rate in general, or at least, and also frame rate increase if you reduce the number of lines that you're reading out. And when it comes to robustness, in a way, we talk about HDR techniques, so being able to cope with reflections and different levels of light, shadows as well as highlights. So it's important that the image sensor also takes care of that. If we then look to the products that we see on the market, we have like two popular solutions, I would say, today. On the left, you see the GMAX 2509, which is obviously a global shutter sensor with a very small pixel, 2.5 micrometer, but that has the advantage that you can have quite some resolution, 4K resolution in this case, horizontally in a relatively small pitch, running at fast rates of 290 frames per second. So that kind of check few of the boxes of the specifications. When it comes to robustness, you will still have also like HDR modes, where you have a different exposure time for odd and even rows, which allows to compensate for the dynamic range that you have. If you then talk about some other, maybe less specification kind of things, where Gpixel tries to address this market, quite a lot of these laser triangulation developers, they request different options when it comes to the cover glass lid of the sensor, like either a very thin glass or an option to remove the glass to avoid interference of the light. So this is something that at Gpixel we try to address, as well as to offer different microlens options. And usually you have like a microlens on a pixel to increase the quantum efficiency, but if your light comes in under an angle, the efficiency of the microlens decreases quite a bit. So either you then shift the microlens to compensate for the angular, or you actually have sensors without microlenses. So that's something we try to accommodate to as much as possible. And then on the higher end, we have a sensor with the similar horizontal resolution, also 4K, but a bit bigger pixels. So that allows a higher signal-to-noise ratio measurement, and also a much faster frame rate. So there we go up to close to 2000 frames per second in 8-bit mode, full resolution. Also there we have special HDR techniques, so not only different as in the previous sensor, we have per line we can do readout in dual gain, so we have high gain, low gain for highlights and lowlights, as well as what we call a multiple slope, so a non-linear pixel response. And similar as the other one, we have options with different microlenses and glass lid options and so on. Then going forward, we have the second 3D imaging technique, which is called structured light. So it's also something that is used quite a bit for high accuracy applications. So it's not projecting a laser line, but a pattern onto an object. And then by the distortion of the pattern by the object, you can then extract the 3D information of the object, basically. So this is quite widely used in what we call 3D AOI inspections, so think about PCB inspections and so on. And it gives some advantages versus like laser triangulation application. I think we have in one shot you actually have a 3D image, so you don't have the need to pass the objects across the laser line, and you have a high level of performance and flexibility. If I'm not mistaken, Basler had a very nice demo of that one there. Not using our sensors, but who knows in the future. Yeah. So if we then look to the sensor specs, it's of course similar, but there are a few differences versus laser triangulation. It's also global shutter, but it's typically a area sensor, which kind of a 1-to-1 ratio, where preferably high resolution, because the higher the resolution, the higher the depth resolution as well. Similar requirements when it comes to signal-to-noise aspects, and thus resulting to larger pixel sizes and certain requirements on the full well. Again, there, of course, the faster the sensor, the faster you can measure. So there are some requirements on frame rate, and similar, again, robustness that translates then to high dynamic range stuff. For this technique, we have two sensors which are used quite widely today. 65 megapixel product, so high resolution, with 3.2 micrometer pixels, running at moderate speed in our world, 70 frames per second in 10-bit mode. And also with high dynamic range options. And one of the later products that we developed is a similar optical format, but lower resolutions, bigger pixels to have higher sensitivity and larger full well, which is then resulting in higher signal-to-noise ratio, but also significantly higher speeds. So that's really for high throughput applications, that's a better option. Also, this sensor has an option for a dual gain readout to increase the high dynamic range capturing. Then the third option that we offer at Gpixel for 3D applications is time of flight. Time of flight is in development for many years, so there is a lot of actually improvements done the past years, especially driven by the mobile phone industry. So it's a totally different technique as the other ones. So you basically send a pulse of light to an object, which gets reflected back on the object and then captured again by the image sensor. So it's very dedicated, and it's very important that you have a perfect synchronization when you send out the pulse and when you measure it again. So these are sensors which are actually also global shutter sensors, but very fast gating, so that you can have a very accurate time measurement. And we talk here about gate periods of nanoseconds, so it's really very fast. So it means it's a dedicated sensor development. One of the advantages is that you also have real-time 3D at several distances. So that helps a lot. It's a complex system, but can be quite compact, typically with small sensors. We also have a few disadvantages. You have not so much accuracy, so it's not really used to measure something, but really to see a shape of an object or to see if something is there or not. So it's a little bit different applications. Typically low resolution, so now we have up to VGA resolution only. And of course, since you try to measure a pulse that comes back, there might be influence of ambient light actually. So if you then look to image sensor specifications again, you need actually a global shutter with different taps to measure the time of flight, time pulses, etc. So it requires really a very specialized pixel design with very fast gating times, as I explained. And because of those fast gating times, these days time of flight is already using what we call backside illumination combined with stacking, so stacking two wafers to each other to really achieve transfer speed of 5 nanoseconds inside the pixel and so on. So it's quite complex, and of course also frame rates are important, but there we typically talk about frame rates of 30 frames per second and so on. So that's this description, and also here we have a solution which we recently launched, which is our GTOF 0503, which is a VGA time of flight sensor with 5 micrometer pixel. So as I said, with BSI, wafer level stacking. And we achieved modulation frequencies, which is a measure of the accuracy of time of flight of 165 megahertz, with transfer times which go down to 3 to 5 nanoseconds, which are, as far as we see, quite state-of-the-art in industrial imaging and even on mobile phone applications. Of course, typically it operates in near-infrared light, so we have still 24% QE at 940 nanometers. And we achieve, depending on the modulation frequency technique, either 30 or 60 frames per second. And then from an operation point of view, we have like several possibilities to do binning and flipping and so on. So this is a short description of what we have today. Obviously, we are doing some R&D as well to further improve the performances. And typically, if you talk about R&D on image sensors, you talk about front-side illumination, back-side illumination, and so on. So most of the sensors that you see here in industrial imaging, they are all what we call front-side illuminated. So you have the light coming in from the top, then you have your circuitry, so metal connections, then going down to the pixel only. So that, of course, limits the specifications you can achieve, especially when pixels become smaller and smaller. So actually what they start doing, mainly driven by, again, mobile phone industry and imagers for that, is what they call backside illumination. So you have, you flip your wafer and your light comes in from the back, meaning that the metal connections are not longer in the optical path going to the photodiode. So that obviously gives quite some improvements. You can make smaller pixels to begin with, but also more complex pixels because your metal connections are not longer in your optical path. And then the next generation actually is what they call wafer stacking. So then you have a combination of backside illumination, but then you stack the first wafer to a second wafer. So in the second wafer you can actually implement digital logic and functionality and so on. So that really make sure you can further improve your pixel performance as well as adding additional features on the image sensor itself. And that gives quite some opportunities. So as you see here, today we still have products in front-side illumination like the G-Sprint, and we have already existing products which are using BSI and stacking like the GTOF sensor. To give some concrete idea is that for stacking what we can do there further is, for instance, implement dedicated algorithms when it comes to 3D processing on the imager itself to reduce the bandwidth from the image sensor to the FPGA, and especially also from then the FPGA to the further system. So that really helps there to make things even faster and optimize data processing and heat management and so on. You can also add further applications like memories on chip. So you can store images, you can sum images, subtract images, you can do a lot of additional features. What you see here is also one of the next generation products that we have in the meantime, not yet announced publicly, that's using this technology. So as a conclusion, what we have, I think for 3D, I think that's already clear for the many presentations. There is no one-fits-all solution. So there are many different techniques, and at Gpixel we are trying to address the different techniques with different products. So over the past we did improve the performance quite a bit, and we are still planning to do that further with embracing new technologies and so on. I would say come by and visit us, but that's probably going to be too late, close to too late. So anyway, you always feel free to contact us anytime. Thank you.
Yeah. Thank you very much, Wim.
You're welcome.
That was a very good overview about the technologies and the sensor development in your company. We are running out of time a bit, and there are no further questions, so your presentation seemed to be clarified all questions, so thanks a lot again.
Welcome, thank you.
Okay.